this semester. I'm Peter Bartlett, the Associate Director of the Simons Institute for the Theory of Computing. We established the Karp series to celebrate the pioneering role of Simons Institute founding director Dick Karp in theoretical computer science. And we're grateful to the many contributors to the Richard M. Karp Fund who made this series possible. The series features visionary leaders in the field of theoretical computer science on topics associated with current programs running at the Simons Institute, and it's geared towards a broad scientific audience. This semester, the Simons Institute's hosting 2 online programs, one on probability geometry and computation in high dimensions, and one on the theory of reinforcement learning. And I'm delighted to welcome our speaker today, Professor Ronitt Rubinfeld, who's participating in the program on probability geometry and computation in high dimensions. Ronitt is the Edwin Sibley Webster Chair of EECS and a member of CSAIL at MIT. She's famous for her work on property testing and sublinear time algorithms, algorithms that can give an accurate output after seeing a vanishing fraction of their input. And she's won an array of awards for her research and actually for absolutely everything she does. Awards for teaching, for mentoring and advising, for inclusion and diversity. She's a fellow of the ACM. She's been a speaker at the International Congress of Mathematicians, and this year she was elected to the American Academy of Arts and Sciences. And Ronitt has a strong Berkeley connection. She's got a PhD in CS from Berkeley. She's also a member of the Scientific Advisory Board of the Simons Institute, and we're very grateful for her contributions there, of course. So today we're delighted to have her presenting a talk entitled, "Is Your Distribution in Shape?" Welcome, Ronitt.
Thank you so much for that really generous introduction. And so I want to talk about distributions today. And in particular, I want to talk about what do you do when you get samples from a distribution over a very large discrete domain. Okay, so here's the model. You get samples from some distribution, let's call it P. You can press a button, you get another sample, and we're going to charge you per sample. And we're assuming that these samples come over some discrete domain. Maybe the numbers 1 through n, or maybe some other domains that we'll talk about later. Okay, but the main thing is this domain is big. Okay, so there's some probability distribution underlying these samples, but we don't know it. So we're going to use P sub I to denote the probability that P outputs I, but this is the part that we don't know. All we can get are samples. And furthermore, we have no assumptions on our probability distribution. So, you know, you may say, I'm assuming my distribution is Gaussian-Lipschitz. Maybe it is, but we're not going to be able to assume that in this talk. Okay, it's the kind of thing we want to actually test. So given samples of a distribution, what you need to know, lots of things. People want to know what's the entropy, what's the support size, how close is the distribution to uniform? Is it Gaussian? Is it Zipfian? What's the number of relevant variables? Lots and lots of questions, and these questions come up all over in statistics, information theory, machine learning, databases, algorithms, physics, biology, all over the place because they're fundamental questions. Okay, so this is a talk about shape, distributions, and shape. So what do I mean? I don't mean did your distributions do the coronavirus workouts every day? I'm asking more about distributions that are in some sense defined by their shape. And this is not a sense that is, I don't have a formal definition for what it means to be a distribution defined by shape. But here's some examples. So you could talk about monotone decreasing distributions where the probability of element I compared to the probability of element j depends on the relation of I and j. So the distribution is getting smaller. You could talk about t-modal distributions where the distribution goes up and down at most t times, or you could have distributions that are well approximated as k-histogram distributions. This is sometimes called k-flat, or k-piecewise constant distributions, where you can represent them in a very compressed manner. Or Poisson binomial distributions, which are really just distributions that are sums of independent random variables, but they may not be identically distributed. Log concave distributions. So there's lots of families. And you might ask, you know, why are these shape distributions? I hope to convince you that we can actually look at them all in the same class soon. Okay, and the key question for this talk is how many samples do you need in terms of the domain size, which we're going to use n to denote. Okay, and in particular, do you need to estimate the probability of each domain item in order to figure out if your distribution has these properties? Or because the problem there would be learning an arbitrary distribution in L1 distance is known to require theta of n over epsilon squared samples? Or is there some way that the sample complexity can be sublinear in the size of the domain? So that's the hope. And in fact, we're going to see that for these problems, the sample's complexity can be sublinear in all of the cases that I talked about. Okay, so let me just start with, I need to give you the example of the uniform distribution. It's the most basic shape property, and we're going to use it later in the talk. So just pay a little bit of attention now. But suppose you want to play the lottery. Your most basic question is the lottery actually uniform? So how would you test? You're getting these samples of some distribution. It's discrete. How would you test if it's uniform? Okay, so a true story. There was a Polish lottery, which involved a machine that had 80, like it was a big machine. It had 80 little balls in it. Every day they picked out 20 balls. And it turned out that the initial machine was actually biased. So here's the example. So they did in the first 300 drawings, every day out of the 80 balls, they took out 20 samples. Okay, so it's not IID because when you, exactly, but you can see here that some of the balls were less likely to come out. The balls numbered 50 to 60 had lower probability. And if you know this, then you can make a lot of money on this particular, in fact, people did make a lot of money on this lottery. So this is a case where the domain size is 80 and it's discrete. So it's a very small domain. And you could figure out pretty quickly that there was a problem with this lottery. Okay, but what about the New Jersey pick 3 or pick 4 lottery? I say this because when we started working on this 20 years ago, I was in New Jersey. And we looked at the pick 3, pick 4 lottery. The pick 3 lottery, you pick 3 digits in order. Pick 4, you pick 4 digits in order. The domain size is respectively 1,000 and 10,000. Let's assume each day was independent. And when we did this 20 years ago in 2000, the pick 3, we had 8,522 past results. And if you ran it in the chi-square test on Windows 2000, it gave you 42% confidence of uniform. Pick 4 was worse because I had fewer results, only 6,500 results. And note that the domain size here is 10,000. So chi-square test on Windows 2000 gave no confidence. All right, so we'll see in a few minutes if maybe Windows 2000 was being ultra conservative, but it wasn't clear there because the number of results that we had to look in past history was a lot less than the domain size. Okay, so here's the problem that we want to look at right now is the sample complexity of distinguishing the case where your distribution P is actually the uniform distribution from the case where P is epsilon far in L1 distance from the uniform distribution. So L1 distance is just the sum of the distances of each element. Okay, and it turns out that this is actually square root n over epsilon squared. Okay, so this is something much smaller than n. And why do you need square root epsilon? What's a lower bound? Well, think about the uniform distribution on n, and then think about the case where you pick a random subset of half the elements and put the uniform distribution on those half of the elements. Now, any algorithm that distinguishes samples from either the total uniform distribution or uniform on half the elements, how is it going to tell the difference? Like if it looks at the names of the elements it sees, the names don't mean anything because these guys in this side on the uniform on half the elements, they were picked randomly. So the names of the elements mean nothing. The only thing an algorithm can do is actually look at the collision statistics. Okay, but there are no, okay, where do we go here? Okay, there are no collisions until you get around root n, say root n over 2, root n over 4 samples. You won't see any collisions in either case. In both cases, it'll look to you like you're just seeing completely random domain elements coming at you. Okay, so you can't distinguish these two cases in less than omega of root n samples. So that's why root n is required. The surprising thing is root n is actually enough. Okay, so there's a whole long history. Let me just say, people, I don't want to get into it too much now, but just let's say people looked at counting the number of collisions. People looked at counting the number of distinct elements in the sample. There's even a version that's similar to a chi-square test that is actually optimal for all settings. So maybe those Microsoft people were being, the Microsoft 2000 people were being super conservative, didn't need to be. And they're even more surprising, there's something called a plugin tester that works. And this is actually the best. So it actually operates by trying to learn the distribution, but how well can you learn a distribution based on just root n samples? Terrible, but still it's good for this problem. So the summary is root n over epsilon squared samples is what you need, and it's good enough. All reasonable algorithms work well, but plugin is the best. Okay, so I just wanted to say that's the complexity here. There is some not so great news that I need to mention. And because that was the problem of distinguishing a completely uniform distribution from epsilon far from uniform. But what if I want to distinguish, what if I know that the uniform, that it's not uniform distribution? I want to distinguish epsilon close from much further. Okay, so I want to distinguish the case where I know that P is not uniform, but I think it's epsilon close. I want to distinguish the case where P is very close to uniform from very far. Okay, and it turns out this is a much harder problem because I have to accept distributions that are only epsilon close, epsilon 1 close. All right, so this problem becomes something like theta n over log n, still sublinear. It's still better than learning, but it's a lot worse than in the other case. We call this the tolerant version, and it tends to be harder. Okay, I also want to mention there's a related question. We just looked at the problem of testing whether P is uniform, but what about another distribution, Q? Okay, let's say you write down Q for me. I don't need samples of Q because I know Q. Okay, it's a specific distribution that we care about. Now, what is the complexity of testing where P equals Q or P is far from Q? Is it like uniform? Turns out, yeah, it's exactly the same. Okay, so it's exactly, it doesn't matter that Q was the uniform distribution. It could have been any distribution. It's also root n over epsilon squared for the non-tolerant version and n over log n for the tolerant version. We call this testing identity for some historical reasons that I can't really defend. Okay, so there's a lot of history here too. And the summary of that is you can use chi-squared like estimators, you can use collisions, you can use reductions to uniformity testing. So there's a lot of ways of doing these things, but everybody gets to root n over epsilon squared. Okay, so here's, so here's the point. I want to talk about monotone distributions. So what do I mean by monotone distribution? Well, let's look first at totally ordered domains. Okay, domains like 1 through n. In here, I'm going to talk about, I'm going to be a little confusing, and I'm going to talk about monotone non-increasing distributions. So these are distributions where if I is less than j, then p sub I is at least p sub j. Okay, and this is a totally ordered domain. So the domain element is the numbers 1 through n. Okay, so these are monotone decreasing or at least non-increasing. Later, I'm going to flip this on you and things are going to become increasing. So just to make sure you're awake, I guess. Okay, so we want to know what is the complexity of distinguishing a distribution P that's monotone from the case where P is epsilon far from monotone. Okay, so that is the question. And it turns out that testing monotonicity requires at least root n over epsilon squared samples. Okay, so it's it requires at least as much as uniformity, because a monotonicity tester would give you a uniformity tester with the same sample complexity. And since we have a lower bound on uniformity testing, we get a lower bound on monotonicity testing. Okay, and to see this is pretty simple. Here I have monotone P. I can look at P and P reverse. Okay, so if I want to test if P is uniform, all I need to do is check if both P and its reversal, that is, what I'm going to do is relabel all the input domain so that a reverse, I'm going to relabel n to be element 1 and n minus 2 to be element 2 and so on. So I have P, and now I've reversed the names of the domain elements. So this is P reverse. It's the same thing, but just backwards. If P was close to uniform, then both P and its reversal should be close to monotone. So you see this P is very far from uniform, and in fact, its reversal is not close to monotone decreasing. Okay, the only way they could both P and its reversal be close to monotone decreasing is if they were actually uniform. And you can quantify this, you can quantify how close they are and show that it's related to how close P is to uniform. All right, so we have a lower bound. We know that testing monotonicity is at least as much as uniformity testing. That's why I had to tell you about uniformity testing first. But maybe it's much harder than uniformity testing. And it turns out it's a little bit harder than it turns out that we actually don't know. Maybe it can be as hard as, but here's open question number 1. Can you do it in root n over epsilon squared? Okay, but what we do know is root n is the right, pretty much the right dependence on n up to polylogs. And actually, Gouleakis, Diaconicus, and Cerverio got it down to a single log n that you have to get rid of, and polynomial in 1 over epsilon many samples. Okay, so I want to say a little bit more about this. One of the main ideas used in this algorithm is to look at something called the Berger buckets, and it's a way of partitioning the domain into segments that are exponentially increasing. Okay, so these are segments that increase exponentially. They look like 1 plus epsilon over a constant raised to the I. So the first few buckets might have just 1 element in them, and then 2, and then they start to take off. Okay, sort of like coronavirus, I guess. But and in total, we'd have 1 over epsilon times log n many buckets. So not that many buckets, just 1 over epsilon times log n. And the interesting thing is, if P is monotone, then when you construct something called P hat, okay, so P hat is going to be just like P. If you look at the bucket level, it's going to give exactly the same distribution weight to the distribution that P does to each bucket. But what P hat will do is spread it evenly along the bucket. Okay, so if this green line is P, then this pink line is P hat. It's just going to take everything P gave to the bucket and spread it uniformly. Okay, and what you can show for this kind of P hat, and this is true only for monotone P, then P minus P hat has to be close. I mean, it's not true only for monotone P, but for monotone P, then P hat has to be close to P. Okay, so basically, we have this really nice way of partitioning the domain, and it's super nice because it's oblivious. You don't have to take any samples of the distribution to figure out how to do this partition. It depends, you see, only on epsilon. Okay, so it's a super nice partition, completely oblivious. And we now have this P hat that we can define. It just has to figure out what weight P gave to each partition, and then it gives it distributes that weight uniformly over the bucket. Okay, but same conditional probability per bucket. And if you do this, then a mathematical proof will show you that P minus P hat is going to be at most epsilon in L1 distance. All right, this immediately gives you a learning algorithm for monotone distributions on 1 through n. So this immediately gives you a way of learning, because all you have to do is learn the weights of each bucket. Okay, so you only have 1 over epsilon times log n many buckets. You need something like 1 over epsilon squared samples per bucket to learn the weight. And that gives you a log n over epsilon cubed sample complexity for learning monotone distributions over 1 through n. Okay, but this is a talk about testing. So the hope is now maybe we can use a learning algorithm to give us a testing algorithm. Okay, so here is a plan for a testing algorithm. We're going to learn this P hat, just as we said. Based on the Berger approximation, we're going to estimate the weights of the buckets. But we're learning this P hat. Remember, I just want to point out something. We have this theorem here only for monotone P, and we're trying to test whether P is monotone. We actually don't know if P is monotone. Okay, so we can learn as much as we want, but if P is not monotone, then all bets are off. This P hat may not be close to P. We have no idea. right? So if P was monotone, P hat will be close to P and everything's great. If P is not monotone, P hat could be anything. We have no idea. So let's learn P hat, estimate the weights of the buckets. Let's check that P hat is close to monotone. It might not be exactly monotone, even for the uniform distribution. Because of sampling errors, you would expect that these average bucket weights might go a little bit up or a little bit down, but you can just check that it doesn't go too crazy. And you don't need any further samples to do this. You basically have log n averages. LP or brute force on a problem of size log n would give it to you. And this is just a computational problem. Okay, and then we need to test that in fact this P hat that we've learned that's close to monotone is also close to P, because it could be that P was totally far from monotone. And the P hat we learned from P is close to monotone, but P was not close to monotone. And so we need to test, in fact, that P hat is close to P. Okay, and the issue here is we might need some tolerance. And if you remember, I told you before that we can distinguish P hat and P, if we can distinguish the case when P hat and P are identical, which they won't be here in general, from the case where P hat and P are epsilon far in root n over epsilon squared samples. But to distinguish P hat and P epsilon close from P hat and P at 2 epsilon far, that already can take n over log n samples. So there's a tolerance issue here, but it turns out that in this specific case, you can actually test that P hat is close to P in root n over epsilon squared. Okay, so there's a paradigm here where we learn the distribution under an assumption, check this learned thing is close to the property we want, and then we test that what we learned is close to our original distribution. Okay, so that is the plan here. Okay, and now I want to talk about some work with Clement Canon and Ilias Diakonikolas and Temis Gouleakis on testing via shape, which takes this paradigm and extends it further. Okay, so all these distribution families defined by shape, such as the ones I showed you, K-flat distributions, log concave, PPDs, T-modal, they are all functions where we can describe them as combinations of K-flat functions. Okay, so I remember K-flat is the same as K-histogram, and it's the same as K piecewise constant. I'm going to use the name K-flat because it's the fewest letters, and it's the easiest to say. So we're going to use K-flat functions to approximate these classes, and we're just going to have a general paradigm where we're going to show that any one of these distribution families that we want to test can be approximated by, say, an order log n flat distribution. Okay, so any T-modal distribution or any monotone hazard rate distribution can be approximated by some T log n flat distribution. And so our generic algorithm strategy will be find a K-flat partition of the domain. Unfortunately, we don't have a non-adaptive way of doing that like we did for monotonicity, but there are algorithms, such as in Batu, Kumar, and myself, of finding a partition adaptively. And then we'll estimate the weights of the K-flats, as we did before. And then we'll test that our learned K-flat distribution is close to our original distribution. Okay, so this is sort of a general paradigm. And then in the end, we have to check also that our concise approximation is close to having the property. And that is usually something that is a computational problem as opposed to a sample complexity problem. So no new samples are needed here, but you need an algorithm, usually some type of linear program. Okay, so this type of paradigm has been applied, can be applied in the paper with Clement, Ilias, and Temis to all of these function family, probability distribution families, monotone K-modal, log concave, monotone hazard rate, binomial, Poisson binomial, K-histograms, K piecewise degree polynomials, K sums of independent integer random variable values. So it gives you one paradigm for all these different classes. And it either, these have all been studied before, so it either gives you the same sample complexity or improves on the previously known sample complexities. And one thing I should say is Acharya, Gouleakis, and Kamath have a completely different paradigm, which is not shape-based, and applies to exactly the same classes. So, okay, so that's what I want to say about that. So now I want to talk about testing monotonicity of distributions over general posets. What we talked about until now is the total order poset. Okay, so it's a total order. Now, what if you just have partial orders? Okay, so monotone distributions over, let's talk about some general poset domains and what we mean by monotone over these. We're going to represent our domain as a graph. So each domain element will be a node. We'll have n nodes, and we'll have directed edges between node u and node v if u is less than v in the partial order. And we'll say that given a distribution p over the nodes, this p is monotone if for every edge uv, p of u is at most p of v. Okay, so this is so I've just to point out that I flipped the direction here, because before we had non-decreasing, so I think we had things were decreasing, and now things are increasing. Okay, so that's in case that's confusing. All right, so lots of works, I'm given a bunch of examples down here, have considered specific posets, and I'll say a bit more about them. This is the line poset that we just considered, and we saw that that was theta tilde of root n. People have looked at grids and noticed that the sample complexity gets exponential with the dimension of the grid. The matching poset is kind of a strange poset, and you might wonder why anybody would look at that. I hope to convince you that it's at least a little bit interesting. It just takes domain elements, pairs them off, and puts an arrow between them. And then there's the hypercube poset, which is what I'm going to spend most of the rest of this talk discussing. Okay, so the matching poset, by the way, is, we know the complexity of testing whether distributions on the matching poset are monotone. It's theta of n over log n. For the hypercube, we have a lower bound of n to the 1 minus theta of square root epsilon, and an upper bound of n over log n. For testing, and that's what I want to talk about, is these two. I'm going to say a little bit about these two results. Okay, so let's just make sure we're in the same page about the Boolean hypercube domain. The hypercube domain, it's Boolean, so we're viewing each node as a d-bit string, okay? And so the size of our domain is 2 to the d. Okay, and we're going to say that x is less than y if the ith bit of x is less than or equal to the ith bit of y for every I. Okay, so in this is typical to make a picture of these. This is the dimension 3 hypercube. It's typical to draw a picture with the all 0 node on the bottom and the all 1 nodes on the top, and you put arrows between nodes that differ in exactly 1 bit. Every time a 0 goes to a 1, you put an arrow. So here we had 0, 1, 1. The first 0 went to a 1, so we put that arrow. Okay, and now I'm less than or equal to anything where I have a directed path. Okay, so that's the notion of partial order on the Boolean hypercube domain. This more generally, we could have D levels, and we draw it kind of like this. We typically put all the nodes at that have the same number of ones on the same level. So level 0 is the all 0, level D is the all 1s, and level I has I 1s and D minus I 0s. Okay, so what about testing distributions for monotonicity over the Boolean hypercube? And it was known, actually, a somewhat general bound for testing monotonicity of poset distributions is that if the underlying poset can be decomposed into a union of W disjoint chains of length L, then you can get this weird bound of O tilde of the width times square root the length as a testing bound. And that, never mind how that works, but that yields for the hypercube slightly sublinear time testing result. Okay, it's actually 2 to the d is the number of nodes in the hypercube, and that's divided by d to the 1/4. Okay, so that's what we get. We're going to get a somewhat better bound right now. But I just want to mention that because there are somehow this lemma is not specific to the hypercube. It is good for any poset, so sometimes it could be useful. But let's go back to our learning to testing regime that we talked about earlier. Again, we wanted to learn some sort of approximation to our distribution, assuming that P was monotone. We want to check that this thing that we learned is close to monotone, and then we want to check that this thing we learned is actually close to our original distribution. So to do this, we need to have a way of learning monotone distributions over the hypercube. So the question is, can we learn monotone distributions over the hypercube in sublinear samples? So we saw a way of learning monotone distributions over the total order with sublinear samples. But what about the hypercube? Because that Bourget decomposition doesn't hold. Okay, and in fact, there's a lower bound of omega 2 to the 0.15d samples that's implied by something called Telegrand-like distributions, which I might say more about later, but it's not that important. It's just a family of distributions that we know we need some, it's going to be exponential in the dimension, okay? So it does not rule out sublinear time lower bound. I mean, we might have an upper bound that's sublinear, but it does say that the learning problem can't be made, say, polynomial in the dimension for hypercubes. Okay, so, okay, but I'm going to show you a learning algorithm for the hypercube, which is still exponential in the dimension, but it is sublinear in the domain size. Okay, so it's the domain size is n, and it's divided by 2 to the log raised to the 0.2 n samples. So it's slightly sublinear, but it's better than what was known. Okay, and then given this, we're going to learn our p hat. We're going to check, we're going to learn our p hat, check that p hat is close to monotone. Again, no further samples will be needed. Our algorithm here is not going to be sublinear time. This thing that I'm showing you today is sublinear samples, but not sublinear time. Sublinear time for this problem is actually open. But so this step we can't do in sublinear time, but then we will test that p hat is close to p. And here we're going to need tolerance. So we will need to do this with the n over log n samples method of valiant and valiant. So all in all, this is going to give us this n over log n dominates the time for the learning complexity. So overall, this will give us an n over log n sample monotonicity testing algorithm. Okay, and if you can get a better way to test that p hat is close to p, then maybe you could get a better overall because this is more time than we need to learn p hat. So this is the dominant step. Okay, so that's how we want to use it. So I want to say something about this learning algorithm for monotone distributions over the Boolean hypercube. And in order to do this, I want to define a notion of tight and slacky elements. So if I have a monotone function, even a distribution, then monotone means that the function value at x has to be at least the maximum of anybody that precedes it, any y that precedes x, f of y. Okay, so this has to be true for it to be monotone. That's the definition of monotone. We're going to say x is tight if we have equality here. So that means the value of f of x is exactly what it needs to be as big as its predecessors, but no more. That's a tight input, x. Okay, otherwise we're going to say x is slacky. All right, so let's do an example. Well, let's take a distribution p that's uniform in the upper half. So it's probability 2 over 2 to the n on the upper half and 0 on the lower half. All right, so let's take somebody right in the middle row. So it's one of the ones that's 2 over 2 to the n, but it's above all zeros. Okay, so we have an element of weight 2 over 2 to the n. Everything beneath it is 0. So this is slacky. Okay. But if I picked an element that was either well into the red area or well into the white area, these guys are tight. Okay, because they're exactly equal to the maximum of their predecessors. Okay, another example, so that's a tight example. Another example is this is what we referred to before as the Lagrange functions. These correspond to a DNF minterms, which is why it's interesting in complexity. So these points here, once you set these to non-zero, everything above it has to be at least their weight. But these guys being non-zero are slacky because they're big, all their children are 0 and they're positive. So they're slacky. Everything above it is determined by its value. Okay, so these are what we call the Lagrange functions. And that's another example. But notice here, there's very few slacky elements. All right. So why are we interested in slacky versus tight? Well, as a motivation to this algorithm, there's a beautiful lemma by Blaise, Hastad, Servedio, and Tan, which I'm going to restate. And this is actually for they developed this lemma for a complexity theory reason. And it was in CCC. They considered monotone Boolean functions. And what they said is, let's say I have this function f, and it's got slacky places all over the place. I can clean it up so that it's slacky on only very few possible levels. Okay, so I can write f as approximating, it's approximately some g, function g, which is slacky on only a constant number of special levels. And this constant, it's independent of the domain size, it's independent of the dimension d, it only depends on epsilon. Okay, so very few places where we have these slacky points where actually the distribution bump or the function value bumps up more than it needs to be monotone. All right, so we extend this to distributions. We have to get something a little bit stronger. In particular, we have to bound the total weight of these special levels where the slacky stuff happens. But that's with this strengthening and this extension to distributions as opposed to Boolean functions, we get a very similar type of lemma in kind of philosophically at least. And let me show you how this lemma can lead to the algorithm. So let's assume that we are in between slacky levels. Okay, so basically between slacky levels, I want to claim nothing interesting can happen. Okay, so I have this value x, and the largest predecessor, y, is, let's look at his largest predecessor. Well, x is equal to the value of its largest predecessor because x is tight. So p of x equals p of y. Everything in the middle, since p of x is equal to p of y, has to have the same probability value. Okay, well, what does that mean? It means that when we take samples of our distribution, if we take enough samples so that we hit this, then we're going to fall into this green area, and we can estimate the total weight of this green area. And if we can estimate the total weight of this green area, then because p is constant in this area, we actually know a good estimate of all the probabilities of domain elements in this area. Okay, so if I know it's constant in this area and it's big enough that I can sample it, then I can know what these probabilities are, or at least a good estimate of all these probabilities. Okay, this is only true for the largest predecessor of x. So if I have another predecessor z that doesn't have as much weight as y, then the weight in the area between x and z is not going to be bigger because I picked y to be the biggest one. So this weight area is not going to be bigger, but I mean, and there's some chance I would confuse z for y only if the probability of z is very close to the probability of y, in which case everything's fine because I will have still a good estimate. Okay, so that's the main idea. We're going to look for all x. We're going to look at all its predecessors on its previous slacky level. These are going to be big little areas, big areas here. We're going to estimate every single one of these, the area between x and y, the area between x and z, and the area between x and any other predecessor on this line, and pick the biggest one and use that as my estimate of the weight of p of x. Okay, that's the whole idea. And the reason we can do this is because we have very few slacky levels. So I have a lot of room here. I have a lot of weight here. I don't need that many samples to fall into this area. Whoops, I didn't want to do that. Okay, sorry. Okay. So I don't need that many samples to fall into this area, hopefully. Okay, so that was the important thing, is I need a lot of space between these points. I need space between x and the next slacky level. Whenever x is far away enough from the slacky level, the green area is big enough that I have samples that fall there, and therefore I can estimate these probabilities. That's all we need. Okay, and that is the basis of the algorithm. So that's the algorithm. It's just what I described. We're going to compute p hat of x. We're going to look at all y such that y is a predecessor of x and y is on the nearest slacky level. And we're going to figure out the estimate of that green area and pick the maximum one. So we'll estimate the green area, divide by the number of points between x and y and figure out the average value. And that's how we'll do it. We'll go through every single point x and do this. So this is not going to be sublinear time, but we will reuse the samples. So we don't need that many samples, but we do need a lot of running time to do this. Okay, so that's the algorithm, essentially. The rough idea for the lower bound is we show an omega n over log n lower bound on a different property, which we're going to call T bigness. Okay, this is joint work with Aliakbarpour, Gouleakis, John Peebles, and R.Yodpinyanee. We look at this property called T bigness, and this property has nothing to do with monotonicity. It just says a distribution has the T bigness property if every domain element has probability at least T. Okay, and think of T as being something like epsilon over the domain size. So everybody, may not be quite uniform, but everybody has some reasonable probability. So it turns out this is a symmetric property. So the valiant work should give you a good lower bound. You can actually get a lower bound via reduction to the to a framework of Wu and Yang, who gives somewhat better dependence on epsilon. And then once you have this n over log n lower bound on T bigness, then you can get a lower bound on the matching poset, the one that we saw before that seemed like a crazy poset. So we can get a n over log n lower bound on the matching poset. And once you get an n over log n lower bound on the matching poset, you can embed that into the hypercube, and that's where you start to lose. And you get some sort of lower bound on the hypercube. So you embed it into a single row of the hypercube. And now what's really important is the min to max value, because everything above the matching poset that you embed into the hypercube has to have at least the value of the top value that you put in, and everything below can be 0. So it's very important, the specific parameters that you can get the lower bound on, but eventually you get some sort of lower bound on the hypercube. Okay, so it leaves a lot of open questions for the hypercube. We don't have a tight bound on the sample complexity. We don't know if you can get sublinear runtime. What happens? Can you extend this to other domains that are like hypergrids? So there's a lot of open questions just on the hypercube. We've looked at a lot of specific posets. I mentioned one lemma that gives you an upper bound in terms of the width and the covering by chains of a poset, but we don't have a lot of techniques in general. But one open problem I want to leave you with is whether there is a sublinear sample monotonicity tester for distribution on any poset. Maybe that's possible. So that's unclear. And in conclusion, distribution testing problems are everywhere. For many problems, we need a lot fewer samples than you might think. And there's a lot of cool ideas and techniques that have been developed, and they've been borrowed from all sorts of different communities. And it's really nice to see how they all fit together. Finally, I wanted to mention that there's a lot more to do. So I hope you all want to work on these problems. And I want to say one more thing, since this is because of the name of this lecture series, I wanted to say thank you to Dick Karp. I was a graduate student at Berkeley when he was a faculty member there, and he taught me a lot. He was super inspiring, and he was very, very supportive, and we all appreciated him very much. And I think he had a big influence on my life. So I really wanted to thank him. And then I want to thank the rest of you for listening.
Fantastic. Thanks a lot, Ronitt. That was really fascinating. So if you want to ask a question, please use the Q&A feature on Zoom, and we'll get to those. While they're thinking about that, Ronitt, I guess I had a question. So the theme throughout has been that you can, estimate a probability distribution of some kind and then use that for the testing problem. But mostly those estimates are exploiting averaging. So for monotonicity, you have this special partition. For the directed graphs, monotonicity there, or on the hypercube, you have this clever approach of averaging over the constant regions. I guess it's surprising. You said early on that the plugin estimator is optimal for uniformity testing. Where there, I don't see any averaging going on. It seems like that's a terrible estimate of the distribution for, order square root n size sample. So what's the intuition for a plugin estimator working in that setting?
That's a good question. I think it's shocking. So I think I'm not the best person to ask on the intuition there. Maybe, is there anybody on this, I don't know if any of the co-authors from that paper are on this particular call, but I don't see any of them. But that's a really that was a shock to me, and I still haven't digested that one. But that's a good question. In general, I just want to caution you about thinking that just because you can learn, you can test. I mean, I know that that's what I'm saying in this talk, and that's sort of my point, but it's not really. I just want to caution. I want a word of caution that, for example, in the Bourget distribution, like even in the monotonicity in the one-dimensional case, if you had a random subset of each of those buckets, you would have had to distinguish that from, like you could have had a distribution that knows the Bourget buckets and picks a random subset of each bucket. Okay, then you're going to have. You're going to learn something, but it's not going to be close to your original distribution. So in some sense, the learning problem can be a lot easier than testing similarity of two distributions. Mm-hmm. Okay, and so what would the tester do is it would have to figure out that you're actually picking a random subset of each bucket. And that's really what the tester, that's why a lot of this is reducing to uniformity testing or some kind of identity testing. But we also inherit the lower bounds from those problems. So usually learning can be easier. Somehow in the hypercube, it was the learning problem that seemed hard because there seemed to be no relationship between what happens in one part of the hypercube and what happens in the other part of the hypercube. And there's lots of parts of the hypercube. But I think your point about that even the plugin estimate for the 1 through n, I think that is really a good thing to understand. And I can't say I have great insights there.
So it looks like Clément has some comments to give. Omid or Jesse, could we shift Clément into be a panelist so that we can hear those comments? I think it's probably much easier than trying to read through those. In the meantime, while they're doing that, Peter Winkler posted a question, Ronnie. Is it the case that the uniform distribution is in some sense the hardest distribution to test for L1 near equality?
I think it's as hard as any. So yes, I don't know of I think that in some sense every distribution is as hard, but uniformity is as hard as anybody. So the valiant lower bound applies to uniform as well. Or at least one of their versions did. So I think, yes, uniform is hard.
Great. And Clement, you had.
Hi. Yeah, so I'm not an author on that paper, but from my understanding, because I was also very puzzled about why the empirical estimator for the L1 distance was a good tester. It is highly biased. So whether you're actually uniform or epsilon far from uniform, that estimator will still be almost 1, but it's like 1 minus little of 1, and somehow between the two cases there's enough of a gap. It's in that lower order term to allow you to test. So it's highly biased, but somehow you can still find a small gap that allows you to get that square root n over epsilon square sample complexity between the two cases, which I find really surprising. And that has good implications, as Ronitt mentioned in the talk, because it's also a test that gives high probability statements with optimal dependence on the probability of error, etc.
Yeah, I agree. I was quite shocked.
Lots of surprises. All right. If there are no other questions, let me say a big thank you again, Ronnie. That was a fascinating and fantastic talk.
Thank you. Thank you so much. It was an honor. Thanks all.